ओके, सो नेक्स्ट टॉपिक है केमिकल प्रॉपर्टीज ऑफ केमिकल प्रॉपर्टीज केमिकल प्रॉपर्टीज ऑफ हेलोएल्केन्स हेलोएल्केन्स केमिकल प्रॉपर्टीज ऑफ हेलोएल्केन्स। इसमें फर्स्ट देखिए, व्हेन वी रिएक्ट दी alkyl halide with strong base or alcoholic KOH, it gives dehydrohalogenation or beta-elimination reaction. Let us take an example, like you are having a alkyl halide CH3 CH2 CH3. Okay, now you are having a alkyl halide, this Br. Okay, now react it with strong base. What are the strong bases which can donate electron are called strong base, है ना, like or normally nucleophiles like CH3O minus, C2H5O minus, है ना. So these are the strong bases, है ना. Like if we take CH3ONA, है ना, so here Na will remove as Na plus and it will form CH3O minus, which is a strong base. So in the presence of strong base, what happens? This is your alpha carbon and this is your beta carbon. Here are two beta carbons are there. So from alpha carbon halogen is removed and from beta carbon hydrogen it removes and it will give you dehydrohalogenation. Dehydro means hydrogen and halogenation, that is minus HX will be removed and it will form a double bond. So our product will be CH3. If we remove the hydrogen from this carbon, so our product will be CH3 CH double bond CH and CH3. Okay, so you will get this product if we remove the hydrogen of this carbon, this beta carbon. Again, if we remove the hydrogen of this beta carbon, so we will get another product, that is CH3 CH2 CH2 double bond, HBr will be removed. So two products we can form, the first product and the second product. Now the which product is more stable? For this we use the Saytzeff rule. So now understand what is Saytzeff rule. According to the Saytzeff rule, we remove the hydrogen of that carbon having less number of hydrogen, है ना? We remove the hydrogen of that carbon having less number of hydrogen. That is, here we can see we remove the hydrogen of that beta carbon having less number of hydrogen. Here we can see there are two beta carbons. So we have to remove, and this carbon have two number of hydrogens, this carbon have three number of hydrogens. So we will remove the hydrogen from this carbon. Okay, so that is why this product will are more stable product. Stable product. One more thing you have to understood that 3 degree gives the most stable elimination, then 2 degree, and then 1 degree. 3 degree gives the most stable elimination reaction, then 2 degree, and then 1 degree. Here, this is the 2 degree carbon, and this is 1 degree carbon. So 2 degree carbon gives more stable product. That is why we will remove the hydrogen from this carbon, because this carbon has here. This carbon has two products both sides which can give the electron, but here this carbon doesn't have the only one side hydrocarbons are there which can donate the electron. Okay, so this is your more stable product. 3 degree gives the most stable product, है ना? Like if we I give you example of 3 degree carbon. Like you having a 3 degree carbon CH3, 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 Br, and react it with strong base like CH3ONA. Now what will happen? This is your alpha carbon. So hydrogen can be removed from this carbon or from this carbon or from this carbon. From any of the beta carbon, hydrogen can be removed, and it will give a stable product. That is, if the hydrogen is removed from this carbon, so the double bond will form here, CH2. This will be CH2, CH2. Okay. So this will become a stable product. Br will be removed from here, and this will be removed. So it gives a stable. So 3 degree gives the most stable product, then 2 degree, then 1 degree, because the carbon having two more components which can donate electron to this carbon. That is why they are stabilizing this carbon. Okay, so you have to remember that 3 degree is more stable, then 2 degree, and then 1 degree. Okay. So next reaction is reaction with metals. Reaction with metals. Okay. So first one is when you react the haloalkane like CH3Br with metal magnesium, it will form a highly reactive reagent CH3MgBr. CH3MgBr. This is also called organometallic compound because here carbon and metal forms a bond. Carbon and metal are forming bond, which is called organometallic bond. Organometallic bond. And the reagent which is formed is called Grignard reagent. Grignard reagent. This is highly reactive reagent, and we cannot store this reagent in open moisture, otherwise it will react with the moisture, that is water, and it will form CH4 plus MgOH-Br. It will form alkane. Okay, so this is also called a Grignard reaction. When we react the haloalkane with magnesium metal, it will form a organometallic bond, that is bond between carbon and metal, forms a Grignard reagent, and if it react with the moisture content or water, it will form a alkane, and MgOH Br. The second one is Wood's reaction. Wood's reaction. If we react this methyl bromide with sodium, it will form alkane CH3 CH, and that alkane is more the number of carbon which are reacting in reactant side, plus it will form NaBr. So this is called the Wood's reaction, where we react the alkyl halide with sodium in the presence of ether. In ether. Why ether? Because sodium is very reactive. That is why we put that sodium in ether. So this is the preparation method of alkane also. So next part is chemical properties of haloarenes. Chemical properties of haloarenes. Chemical properties of haloarenes. So haloarenes usually gives electrophilic substitution reaction. So halogens, so haloarenes gives electrophilic substitution reaction. Substitution reaction. But halogen deactivates the reaction or shows deactivating nature due to minus I effect. Halogen shows minus I effect. That is why it deactivates the ring. Alright. So in electrophilic substitution reactions, haloarene shows halogenation reaction, nitration reaction, sulfonation reaction, and Friedel-Crafts reaction. In halogenation reaction, haloarene means is reacted with halogen X, is reacted with halogen like chlorine in the presence of AlCl3, and it gives ortho and para directing products. As we know that in ortho and para position electron densities are higher. That is why electrophile will get attached to the ortho and para position. So it will gives ortho and para directing halides, where para product is more stable. Next, in nitration, we react the product with nitric acid. So nitrate substitution will get attached like take the haloarene and react it with nitric acid HNO3 in the presence of H2SO4. It will gives NO2 plus electrophile, and that electrophile will get attached in ortho and para position. So we will get ortho and para substituted haloarene. This is called nitration when we react it with nitric acid. Next is sulfonation. So in sulfonation, we react the haloarene with H2SO4. It gives SO3H electrophile. So it will get attached in ortho and para position of haloarene. Ortho and para position. This is called sulfonation. Fourth one is Friedel-Crafts reaction. So in Friedel-Crafts reaction, two types of reactions are there. When we react the haloarene with alkyl halide, it will give CH3 plus electrophile. It will give Friedel. This type of reaction is called Friedel-Crafts alkylation, where the alkyl group is get attached in ortho and para position. This is called Friedel-Crafts alkylation. FC, Friedel-Crafts alkylation. When we react the haloarene with acyl CH3 C double bond OCl, this will be negative, this will be positive, and this electrophile will get attached in ortho and para position. And one thing you have to remember, that para products are more stable, are more stable. That is why they form major product. Major product. So para products are more stable. That is why they always form a major product. Okay. Okay. Next reaction is reaction with metals. Reaction with metals. Metals. First one is fatigue reaction. Fatigue reaction. When we react the haloarene with sodium, take 2 sodium, in the presence of dry ether, it will give you alkane plus anemia it will give you alkane benzene 2N, you take the R's and the R will come. This is called the Fittig reaction when we react the haloarene with sodium metal. The next is Wood's Fittig reaction. Wood's Fittig reaction. In Wood's Fittig reaction, we take the haloarene plus haloalkane and react it with sodium in the presence of dry ether. So it will form hydrocarbon plus 2Na. So one thing you have to remember, when we react the haloalkane with sodium, it will form a Woods reaction. When we react the haloarene with sodium, it will form a Fittig reaction. And when we react both haloarene and haloalkane with sodium, it will form a Woods Fittig reaction. Okay. So these are the electrophilic substitution reactions. Here, nucleophilic substitution reactions shown by the haloarene. Nucleophilic substitution reaction. Substitution reaction. As we know that the haloarenes in haloarenes there is a partially double bond character between the carbon and Cl bond, and because of the partially double bond character, because it shows the resonance, chlorine is having a lone pair electron, so it will donate the electron and the electron will relocalized inside the benzene, and because of the resonance it causes a partially double bond character, and because of this partially double bond character between the carbon and chlorine, it is very difficult for the cleavage of this bond. Normally cleavage of this partially double bond is difficult. Okay. The next thing is, when the nucleophile want to attack in this haloarene, so because it is an electron rich compound and nucleophile is also an electron rich compound, so there will be the repulsion between the nucleophile and the haloarenes. So due to the nucleophile repulsion is also not possible to react to attack the nucleophile to the haloarene. Third is the positively charged phenyl, or we can say electrophile phenyl is not stabilized by resonance. That is why the nucleophilic substitution reaction is normally not possible for haloarene. But only one reaction are there we have to learn, that is Dow's process. In Dow's process, what we do, we take the haloarene and react it with high temperature and high pressure. In high temperature and high pressure, we react it with methyl group. React it with NaOH, sodium hydroxide. React it with at high temperature, very high temperature and high pressure. It gives a phenol So this is the only nucleophilic substitution reaction where OH minus nucleophile will attack to the ring. So at high temperature, at high pressure, it is only possible for this reaction and will form a phenol. So this is the only nucleophilic substitution reaction that is called Dawes process, which is shown by haloarene compound. So here one thing you have to understand, that whenever the electron withdrawing group are attached with the haloarene, like this is our haloarene. When the electron groups are like electron withdrawing group EWG, electron withdrawing group like nitro group, COH group, है ना? When they are get attached with the haloarenes at ortho and para position, they increases the reactivity of haloarenes, and facilitate the nucleophilic reaction. So whenever the electron withdrawing group are attached at ortho and para position in haloarenes, they just attract the electron and reduces the electron density in the ring and facilitate the nucleophile attack. Because the more electron density will in the ring, it will repel the nucleophile and the nucleophilic reaction will not take place. But when the electron withdrawing group are attached at ortho and para position only, not at meta position, because a electron density are maximum at ortho and para positions. So when the electron withdrawing group are attached at ortho and para position, they reduces the electron density of the haloarenes and facilitate the nucleophilic substitution reactions. Okay.